requests on 6 through 10 that they want me to talk about?
Would you be able to do 10B, please?
10B?
Yep.
Sure. All right then. So that seems like a perfect place to start. Doing that will require me to get my head going. Here we go. Okay. So in number 10. So this is what? Worksheet 4.1b, right? So number 10. So we've got a 12 kilogram box. 12 kilogram box. In part A, we figured out that the coefficient of kinetic friction was, is it 0.53, is that right?
It's 0.20.
Oh my gosh, I'm way off.
Maybe I'm wrong.
Nope, you're right, you're totally right, I'm just stupid. Okay, so there's our coefficient of kinetic friction. Okay. Oh, and the problem tells us that the coefficient of static friction, oops, the coefficient of static friction is 0.30. Okay, cool. Yeah.
So, since we found the coefficient of kinetic friction, does that apply to
all three parts?
Oh,
yeah.
Okay, never mind.
Is that what was messing you up?
Yeah, I just didn't know where to find it.
I gotcha. Okay, so maybe this is a thing worth talking about that I think hasn't been stressed yet, you guys. So we keep talking about the fact that the coefficient of friction it's a ratio, right, between your force of friction and your normal force. Okay? And so in the video, when we, whenever it was, back in chapter 3, when we learned about friction, I told you guys that the coefficient of friction was kind of a measure of how rough your two surfaces are. Okay? So even though we experimentally measure normal force and the force of friction to find the coefficient of friction, really that coefficient of friction is determined by the two surfaces that are in contact. Okay? So in this problem, it's the same box on the same surface, so the coefficient of friction doesn't change. In other words, those two surfaces are still just as rough, air quotes. Cool?
Yep.
All right. So is that all you needed from that?
Yep, that was it.
All right. Would anybody like me to finish going through 10B anyway?
Now that I have my stuff, is it when it's below is it the horizontal component that's negative, or?
So when you, all right. So a lot of people are asking about the whole above the horizontal, below the horizontal thing. So above the horizontal just means here's horizontal. So either this or this could be interpreted as above the horizontal. All right. I usually draw this just because that way my x component is positive. Do you know what I mean?
Yeah.
All right. There's no reason why you couldn't draw it this way, but then you just got to make sure that you draw your x component as being negative.
Okay.
Do you know what I mean?
Yeah, I see that.
So either of these two angles could be described as above the horizontal, and then below the horizontal would be either this blue one or this blue one. And again, I would opt in the direction of this just because it makes your x component positive.
Okay.
But it's not wrong to do it the other way. It's just your drawing will be flip-flopped from mine, you know?
So how does it change for like the part A and part B?
Okay, so I'll get there in 1 second. Are you good with that?
Yeah.
Okay. Gigi, you started to ask
I
something?
just have a question.
Yeah.
If you do it the other way, would it be the same answer?
Except, so like if you're finding the acceleration, whatever sign I get on my acceleration, yours will be opposite.
Okay.
Do you know what I mean? So you'll have everything flip-flopped.
Okay.
So if I get an acceleration of 2, you'll get negative 2. If I get negative 5, you'll get positive 5. Yeah, it's fine. Okay, so here's the deal then. So going through, without going all the way through number 10 then, let me just kind of talk in general terms. All right, so the idea is in 10B, Roy is, I've lost my paper again. In 10B, it says, suppose the force was exerted at an angle of 30 degrees above the horizontal. So in part B, the force is 49 newtons at an angle of 30 degrees above the horizontal. Okay? And in part C, it's still a 12 kilogram box, but this time the force, it's still 49 newtons, but now it's exerted at 30 degrees below the horizontal. Okay? And it turns out that the box moves in one situation and doesn't in the other. Which is maybe like, as a quick knee-jerk reaction, is maybe a little counterintuitive, right? Because aren't both of these drawings going to have the same x component of force? right? Because they're both 49 newtons, and they're both 30 degrees off the horizontal. The only thing that's different is one of them is the y component's up, and the other one, the y component, is down, right? But the horizontal component that's trying to make these boxes move is the same in both drawings. So let me pause there for a minute. Does everybody see what I'm saying there? Okay, so if you find those components, the x component ends up being 49 times the cosine of 30 gives you 42.4 newtons. So in both cases, we've got 42.4 newtons pushing this thing. Why does that number not sound familiar? Is that right? That's right? All right. So, but then when you do the math, object C doesn't move, but B does. So can somebody talk to me a little bit about why that matters so much? Sure, we got Sophie. Sophia, sorry.
Because like there's more friction compared to like the normal forces higher.
In which one?
When you're pushing down.
Good, yeah. So remember, you guys, your force of friction doesn't just depend on the coefficient of friction, right? So Ethan was confused about the fact that the coefficients are the same in parts B and C as they are in A. So is everybody okay with that? The surfaces, the roughness of the surfaces hasn't changed. Okay? But the idea is in part C, because this y component is down, it's equivalent to pushing the surfaces down with more force, pushing the molecules tighter together, and thus creating more friction. Okay? Whereas in this drawing, our y component is up. So we're kind of relieving the pressure between the two surfaces, and so decreasing the amount of friction. Okay? So what it boils down to is in this problem, because our normal force is much bigger, there's more static friction available. And in this one, your normal force is smaller, and so there's less static friction available. Okay? Weston, what are you? Sorry, I'm getting my Weston and Dustin.
Yeah.
You good?
Yeah.
Problems, you guys? Okay. As maybe a dumb example, take your calculator, set it down on your table, button side down, because all these calculators have this rubber thing that produces a terrifying amount of friction. Terrifying. Like, it frightens me. I had a nightmare last night about the friction. Friction. All right. So if you take your calculator and set it on the table, you can push it easily, right? Okay? But if you use one of your hands and push straight down on the calculator and then try to slide it, it's way harder. Because when I push down on it, what am I doing? More normal force and thus more friction, right? So that makes it harder to slide. Does that make sense, you guys? Okay. All right. Questions on number 10? Yeah.
Okay, the y value for the like that for y for C.
The y value what?
Like the y value for C is going down, right?
Mm-hmm. Yeah, it turns out to be negative 24.5. So what were you going to ask?
No, that's it. That's it. Cool. Okay.
Good. So what that does is it increases the normal force because it's got to compensate for this extra downward force. Good?
No. The normal force and the what's it called? Sorry, the force of gravity. In these problems, do they always cancel out?
Say that. I think the answer to the question you're trying to ask is yes. But restate the question.
So in these problems, like these ones right here, is the normal force and the force of gravity always trying to cancel out?
Trying to, yes, but you're missing a force. So in this drawing right here, let me do this. Where do I want to do this? So in this drawing, this is kind of a crap drawing, right? So let's clarify this drawing. So here's my drawing. So gravity's pulling down with a force of 12 times 9.8, which is 117.6 newtons, right? Good. Let me move that up a little bit. Okay. We know that Roy is pushing down on it. Oops, seriously? We know that Roy is pushing down on it with a force of 24.5 newtons. And he's pushing forward on it with a force of 42.4 newtons, right? All right, so now talk to me about normal force. So would it be 117.6? No. Okay, so your original question was, do normal force and gravity always cancel? And the answer to that is no, because my normal force here isn't 117.6, right? So the question I was trying to get you to say is, all of your vertical forces are going to cancel, but there are three vertical forces: gravity, normal force, and whatever the y component is from your person pushing or pulling the box.
They'll always cancel out, right?
Those three forces will always cancel out, yes.
Okay, thank you.
Good?
Yeah.
Do you understand what I was trying to get you to realize?
Yeah.
Because when you first asked the question, you didn't say anything about this force.
Yeah.
Cool?
Yeah, I get it.
All right. Everybody good? All right. Anything else on 6 through 10? Okay, then let me do this. Let me run through number 11 real quick, just because I think even though it's not going to be on the test, I do think there's value in it. Let's do it, and then we'll do the target check, and then that's it. Okay, so here we go. So number 11. So let's kind of read through the problem and see what we can get. Well, actually, before I do, so let me ask you guys. So walking around, I think I only saw like 3 or 4 people that got number 11 right. A lot of people wrote a little bit and then were just like, I don't know. All right. So I don't mean this in a snarky way. I mean this in a legit, like there's something I'm trying to get at here. Why was number 11 harder than 7, 8, 9, or 10? Give everybody a second to think about it, and I'll get you. Okay, sure. What do you got?
Because you didn't have all of the information, you didn't know what the force is, so you had to use some variables to plug in.
Okay. Yeah. So in any problem, you never have all the information, right? Otherwise, there wouldn't be a problem to ask. Okay. But there was something sort of specific about what you didn't know in this problem that made this one harder. And so you're right. You got to use a variable. That's a piece of it, but there's a little bit more that I'm trying to get at. You got an idea, Amy?
You didn't know the normal force.
Say it again.
You didn't know the normal force.
You didn't know the normal force. Can you talk to me about why you didn't know the normal force?
Because you didn't know, like, you're trying to find a force, right?
Yeah.
And then do you know the coefficient?
Yeah, I think you know the coefficient. Yeah, it's 0.3.
So you know the coefficient, so you know what the coefficient is based on the normal force. And then since you don't know the force, you can't find the normal force. So
Okay.
you don't really know one.
Yeah, so the problem is the thing that because there's this one thing you don't know, it snowballs into there being a whole bunch of things you don't know. All right, here's what I mean in English. So check it out. We've got this box. It tells you that it's 50 kilograms. So I think just about everybody I saw had gotten this far and then stopped. All right, so that's that, right? Okay? So the question wants to know how much force we need to make it move at a constant velocity, right? Okay, but the problem is the force that we're exerting, let's just call it F. We're trying to find this force, but the problem is that force is exerted at an angle. So there's a horizontal component and a vertical component, right? But without knowing this force, we can't find either of the components, right? So when we come over here to make our drawing, we're kind of stuck, right? Let's draw our free body diagram without any numbers and see what we can kind of come up with. Okay? So gravity's pulling it down. There's a downward force from the person pushing it, right? There's a forwards force from the person pushing it. And so what Amy is saying is this. There's 2 other forces on it, right? In order for it to move at a constant velocity, so that our net force is 0, we must have some friction, right? What kind of friction, you guys? Kinetic, right? But to find the kinetic friction, I need to know my normal force, right? Right? Because kinetic friction is normal force times coefficient. Okay, so great, find the normal force. Oh, well, my normal force is going to depend on these 2 things, right? Like AJ and I, say that 10 times fast. Like we were saying, these 2 forces have to cancel that. But I don't know one of these 2 forces, right? Do you see what I'm saying? So the fact that there's this one thing I don't know on my drawing means there are 4 things I don't know. I don't know the vertical force, the horizontal force, the normal force, or friction. So how am I going to solve this then, right? All right, so here's my recommendation. When you run into a problem like this, and you see this sort of snowball effect of like, well, I need to find this one thing, but that one thing affects everything else, then what I want you to do is I want you to sort of pretend that you know that thing and ask yourself what you would do with that information. Okay? So, in other words, what we're going to do here is we don't know F. Our goal is to find F, right? Oops. Our goal is to find F. We don't know what it is. So let's just call it something. Let's call it F. Okay? So, suppose I told you what F was. What would your next step be? We've already found our force of gravity.
Find the X and Y components.
We'd find the X and Y components, right? So do you guys agree that if I knew F, I could find Fx and Fy? Just using some trig, right? Fx would just be F times the cosine of my angle, right? And Fy would be F times the sine of my angle, right?
Yeah.
Make sense? What's wrong?
Like it's 30, 60, 90 triangle.
Yeah, so you can use 1/2 under 3/2, or you can use sine of 30 and cosine of 30, whatever, it doesn't matter. But so here, let me change these thetas to 30s, I guess, since we knew the angle was 30. All right, so is everybody good with that?
Wait, I have a quick question.
Yeah, please.
Okay, so on the sheet it says if the angle between the handle and the floor is 30 degrees. So I was kind of confused why. Never mind, I think I understand now.
Sure. So
Yeah, I think I
it's like a lawnmower or something with a box on it, right? And
Yeah.
so, I mean, I guess, you know, if you sort of imagine the handle coming all the way down to the floor, it's talking about this angle being 30 degrees, right? So, but those are equal because they're alternate interior angles.
Mhm.
Is that what you're asking?
Yeah.
You good?
Yep.
Okay. All right. So, is everybody good with what I did over here? All right, so let's pretend we knew what F was. So that would mean that our Fx would have been whatever F is times the cosine of 30, and our Fy would have been whatever F is times the sine of 30. All right? Now, if I knew those values, then what would be my next step?
Normal force.
Find the normal force, right? Doesn't the normal force need to be big enough to cancel these two? Right? So these are both down, so they're both sort of negative, right? So this has to be an upward force big enough to cancel the two negatives. So it's got to be 490 plus F sine 30, right? So that's my normal force. Follow? All right, and then one last step, and then from there it's just kind of some algebra. Move this garbage out of my way. Oh no, what just happened? Out of my way, question mark.
I'm sorry.
Why are you being stupid? There we go. What's going on? Oh. Sorry, I'm just trying to buy myself a little room over here on the side of the board. Okay. So we just found the normal force, right? So once you find a normal force, what would your next step be?
Plug it into the equation.
Plug it in to find your friction, right? Oh, well, my friction then is going to be my coefficient of friction, which is 0.3 times this. Yeah.
I think it's just because we're not done with it, but I don't see how those numbers are going to cancel to give you a value for F.
Give me 2 seconds, because I'm like half a second away from finishing it.
Okay.
All right, so before we get there, does everybody kind of understand what I've done so far? I know it's a lot, but follow the train of thought. Weston, you okay?
Yeah.
All right, now, so I'm going to pick on you because you were asking. So what is Roy trying to make the box do?
Go at a constant.
Move how?
At a constant velocity.
Which means that our net.
Force is 0.
So tell me something.
Oh, you add them up, it's going to be 0.
Yeah, add what up?
Well, you can kind of like ignore a normal force.
Good. Yeah, so these two forces here have to cancel each other out, right?
No.
My horizontal forces have to cancel each other out. So in English, what that means is I get f times the cosine of 30, that's this guy, has got to equal this guy up here, 0.3 times 490 plus f sine 30. And then do some algebra and solve for f. Okay? Which looks really intimidating, but remember, you guys, cosine of 30 is just a number. That's like 0.86, right? And sine of 30 is just a number. That's 1/2. So the only variable we have here is f, so it just becomes some algebra from there. I wish we had a couple more minutes. I'd want to solve it. But so anyway, does this make sense? Okay, so that definitely is tough. Like somebody asked, I don't know if it was before or after the bell, this is definitely bordering on AP style. So I wouldn't give that to you on a test. And it's a thing that theoretically I would like to think you guys could do. All right, problems with it? Okay, cool. So I'm going to give you guys a target check. When you're done with the target check, it goes in the basket. Video 4.2 is due tomorrow. It's 23 minutes. The audio got a little funky. I'm hoping that it worked out okay. For some reason, it's been lagging again. I think the computer sucks, is what I think the problem is.